Professor Richard Segall. Dr. Segall is a professor of computer and information technology at Arkansas State University in Jonesboro, Arkansas. He holds BS and MS in mathematics, an MS in operations research and statistics from Rensselaer Polytechnic Institute in Troy, New York, and a PhD in operations research from the University of Massachusetts at Amherst. He has served on the faculty at Texas Tech University, the University of Louisville, the University of New Hampshire, the University of Massachusetts Lowell, and West Virginia University. His publications have appeared in numerous journals. You can read about them in the program. His research interests include data mining, text mining, web mining, database management, and mathematical modeling and supercomputing applications. His research has been funded by the U.S. Air Force, the U.S. National Aeronautics and Space Administration, NASA, the Arkansas Biosciences Institute, and the Arkansas Science and Technology Authority. He is co-editor of a book titled Visual Analytics of Interactive Technologies, Applications to Data, Text, and Web Mining, published in 2011 by IGI Global, and is currently co-editing a book titled Research and Applications in Global Supercomputing, to be published by IGI Global, and has mentioned that he is looking for contributors to that last book that is in progress. So I'd like to thank you for presenting, and Professor Richard Segall.
Okay, I want to thank you for that fine introduction. Okay, the title of my talk, as was indicated, is Computational Dimensionalities from Global Supercomputing to Data, Text, and Web Mining. What is a supercomputer? A supercomputer is a computer at the front lines of current processing capacity and speeds of calculations. They were first introduced in the 1960s. The supercomputers of the 1970s used only a few processors, and in the 1990s, machines with 1,000 processors began to appear. By the end of the 20th century, supercomputers were massively parallel computing systems composed of tens of thousands of processors. In contrast, supercomputers of the 21st century can use over 100,000 processors, including those with graphic capabilities. Sequoia, a third-generation Blue Gene machine from IBM, runs on 1.6 million processor cores. It can reach speeds of up to 20 petaflops. A petaflop equals 10 to the 15th operations per second, which means that Sequoia can perform 20 times 10 to the 15th operations every second. Sequoia requires 3,000 gallons of water per minute to cool it down. It uses 6.7 megawatts on average, with peak usage approaching 9.5 megawatts. 1 megawatt equals 1 million watts, so that's about $6 or $7 million a year in power. Here's a picture of the Sequoia supercomputer at Lawrence Livermore Labs. 6 months ago, this was the fastest computer in the world, and China beat us out in the last 6 months, so I'll show you the list of the top 10. Information quality in supercomputers. The Minnesota Supercomputer Institute in 2012 made a report titled The Effect of Health Information Technology on Quality and Productivity. And a publication in 2013 titled Supercomputing Generated Images Playing Role in Contest stated imaging capabilities represents one of the important components of supercomputing systems. And advanced devices can take extremely large data sets and form that information into pixels that create high-quality images that would be impossible to generate without the help of supercomputers. Generated at the Barcelona Supercomputing Center in Spain, visualization of the human heart was captured the attention of the National Science Foundation, and the visualization of the heart through extremely accurate is not an actual heart, but instead it's a computational muscles that are crafted into the shape of a heart and put into action through simulation from an electrical pulse. The entity beats move extremely similarly to the human heart. In 2012, the U.S. Department of Energy had two early career starts who rose to the data challenge. One is Professor Kelanaram of Washington State University, who stated that supercomputers are designed not only to solve problems faster, They should also scale to solve much larger problem sizes faster. That's what required in data-intensive biological computing and the aspects that differentiates this work. He used map-reduced parallelization techniques that was almost 400 times faster than existing codes, locating the links between 8 million points of protein data in the same time it took an existing serial code to analyze just 20,000 proteins. There was 1.6 million cores that are located on 96 different racks, each of which weighs nearly 5,000 pounds and gives off an average of 100 kilowatts of energy, the amount needed to power about 50 single-family homes in a supercomputer. The current status of the world's supercomputers, the Indian government has stated that it had made a commitment to about $940 million to develop what could be the world's fastest computer by 2017, one would have a performance of 1 exaflop, which is about 61 times faster than today's fastest computers. I have a 7.5-minute video here that I want to show that's on YouTube, and I hope this will work. And this is on the Human Brain Project. You know, even in the 21st century, there's a lot of unsolved mysteries with reference to the human brain, and it's a complicated machine that neuroscientists continuously try to understand. New user? This isn't it. I'm going to maximize it. Can you maximize? Sound.
A 100 billion neurons connected by 100,000 billion synapses. As a billion neurons connected by 100,000 billion synapses. The human brain is the most complex machine we know of, and the most mysterious one.
We face huge issues in neuroscience to understand how the pieces of the brain fit and work together. We face huge issues in medicine to understand how to objectively diagnose and treat brain diseases.
This is a big, big challenge. It will have an enormous impact on the health of the aging. It is really the central project for brain.
Can you just wait here?
And that could revolutionize computing the way we do it today.
The Human Brain Project brings together hundreds of scientists from leading European research institutions. It is one of the most ambitious neuroscience projects in the world.
What we are proposing is to establish a radically new foundation to explore and understand the brain, its diseases, and to use that knowledge to build new computing technologies.
The project is coordinated by EPFL, located in Lausanne, Switzerland. The researchers will systematically study neurons, the building blocks of the brain. They will collect and consolidate all the biological data produced by scientists around the world. They will integrate this knowledge into a massive simulation running on a supercomputer. The result will be the most accurate model of the human brain ever produced.
I'm really thrilled to be part of this and to help neuroscience to have a more coordinated effort, to understand the brain and to exploit the brain, to really use what's in the brain in computational principles and to derive new technologies.
From an original group of 13 institutions, the HBP now encompasses more than 80 partners across Europe.
the human cortex is organized into specialized regions. We need to understand what these different regions are doing. Some are specializing for language, some are specializing for vision. So we will create systematic maps of the human brain, trying to understand each of these subsystems and trying to understand what are the specific parameters so that they can ultimately be brought to simulation.
Brain diseases have become an immense burden in the Western world. In Europe, they cause more than heart diseases, cancer, and diabetes all put together. Scientists will work closely with hospitals to find new treatment to neurological disorders. They will collect medical data such as brain scans in order to develop better ways to diagnose diseases.
It involves trying to make sense of the enormous amounts of data we collect from all our patients and using those data in order to define the disease. And to do that, we need first to be able to bring the data together, so we need databases. And for that, we're going to need really high-powered computers to be able to do what we call data mining.
We now have a blueprint to understand the molecular architecture that defines the development and organization of the human brain. But it also gives us the fantastic opportunity to understand how the DNA mutations that cause hundreds of different brain diseases produce those diseases.
There'll be ways of testing potential drugs where you won't need to use animals, where you'll be able to use something that approaches the human, and where you'll have some information of how good the treatment is going to be to correct the defect.
The simulation of a complete human brain will require supercomputers that are 1,000 times more powerful than today.
The power of today's computers is by far not sufficient to compute this complex system. Of course, we have to pool resources in order to satisfy the huge demands.
The project will stimulate the development of new supercomputers. By understanding how cognition works, it will help to design radically new devices called neuromorphic computers. They will combine the power of microelectronics with the flexibility of human intelligence.
If you want to solve a new problem, you use software. You don't do that in your brain. You learn, and you are able to learn to handle completely different situations, even things that you have never seen before. These are systems that are directly modeled after the brain. So what we build is physical models of brain circuits on silicon substrates.
The Human Brain Project will create a realistic simulation of the brain. This new tool will be used to understand how the mind works, to study brain diseases, and invent new electronics. To achieve this goal, more than 80 European institutions have already joined the project.
The competence is distributed all over Europe, in supercomputing and in neuroscience.
By putting so many different people together and making such a big community, such a big project, we can do things we could never do with any other smaller scale project.
For Europe, this is a kind of a big science project. This, I believe, the 21st century will be the century of the brain.
I think the project is it's a visionary project. And it seems to me that the field needs this kind of initiative really to move forward.
And I see fantastic opportunities in the future.
The technology is at reach and the necessary knowledge available.
It's like holding a giant telescope to peer into deep space. Only then will we be able to look deep into the brain and ask questions that are impossible experimentally and theoretically. It's an infrastructure to be able to build and simulate the human brain, objectively classify brain diseases, and build radically new computing devices.
We have what's called the technology roadmap. We know which technology will be used at which point in time in the project, and the way we will scale up our systems so that they reach the complexity of the human brain.
The Human Brain Project will put Europe at the forefront of neuroscience. It will deliver new strategies to fight brain diseases, and it will revolutionize electronics. But first of all, it will offer a revolutionary new tool to study the most mysterious phenomenon of the universe, the human brain.
Want to get the next slide? Okay, all right. So I showed a video on the Human Brain Project which uses supercomputers. And as the video indicated, even in the 21st century, there's a lot of unsolved mysteries when it comes to the human brain. It's a complicated machine that neuroscientists are continually trying to understand. And it's a new scientific endeavor. It hopes to involve some of the mysteries by creating a high detailed simulation of the human brain. And essentially, researchers will be using supercomputer to build a working replica of our minds. With $1.6 billion in funding, with more than 200 researchers, and he said there were 80 institutions working on the Human Brain Project in Europe, it's the largest, most ambitious cooperative experiment of its kind. Serious hardware is necessary for a project of this type. To pack the simulation to a single computer would require a system 1,000 times more powerful than today's supercomputers. The project began in 2012. It will take Europe 10 years to map all of the 100 billion neurons connected by 100 billion synapses to make up the human brain. I talked about the top supercomputer in the world, and as of last month, June 2013, Tahini-2, a supercomputer developed by the China's National University of Defense Technology, is the world's #1 system with a performance of 33.86 petaflops on the line pack benchmark, according to the 41st edition of twice-year top 500 list of the world's most powerful supercomputers. The list was announced June 17th during the opening session of the 213th International Supercomputing Conference in Leipzig, Germany. And it's also nicknamed the Milky Way 2, which it's deployed by the National Supercomputing Center in Jiangsu, China, by the end of the year. The surprise appearance of this project 2 years ahead of its expected deployment makes China's first return to the #1 position since November 2010, when Tahini-2 1A was the top system. This has 16,000 nodes, each with 2 Intel Xeon Ivy Bridge processors and 3 MPI processors for a combined total of 3,120,000 computing cores. The second top supercomputer in the world as of June 2013 is the Titan, a Cray XK7 system installed in the U.S. Department of Energy Oak Ridge National Labs. It was previously the #1 system 6 months ago, but now it's ranked #2. It achieved 17.59 petaflops on the line pack benchmark using 261,632 accelerated cores. It's one of the most energy-efficient systems on the list and consumes a total of 8.1 megawatts and delivering 2143 metaflops per watt. Here's the list on the web that you can get. If you go to www.top500.com, it lists the 500 supercomputers in the world. You can get an Excel. It allows you to download an Excel spreadsheet with different characteristics about it. And this is a list of the top 10 as of last month of 2013. China is #1 with the National University of Defense Technology. It has over 3 million cores. The second one is at Oak Ridge National Labs in the United States, which has 560,000 cores. The third one is at the Department of Energy, Sequoia, which has 1,500,000 cores. The fourth one is in Japan, the Riken Advanced Institute for Computational Science. The fifth one is at Argonne National Labs in the United States. The sixth one is at Texas Advanced Computing Center at the University of Texas, Austin. The seventh one is in Germany. The eighth one is in the Department of Energy of the United States. The ninth one is at Leipzig in Germany. And the 10th one is at the National Supercomputer Center in China. New supercomputer speeds have allowed cancer genome analysis to be able to be performed in seconds. And on October 3, 2012, it was announced that the launch of a new genomic supercomputer platform that can speed cancer genomic analysis from months to seconds. And it's a result of a collaboration announced in October 2012 between Nant Health, a health technology company founded by billionaire Patrick Soon-Shiong, and several other well-known companies, including Blue Shield of California, Verizon, Bank of America, AT&T, Intel, and HP. The platform analyzes more than 6,000 cancer genomes from more than 3,000 patients with 19 different cancer types in a total time span of 69 hours, or one patient every analysis every 47 seconds. Typically, according to the announcement, genomic analysis takes, without supercomputers, roughly 8 to 10 weeks to complete. So we can't reduce the cost of care and improve outcomes in cancer if we don't have the capability of knowing the right treatment at the right patient before treatment begins. We need a national supercomputer infrastructure that brings genomic medicine into clinical practice. By placing supercomputers in the hands of physicians, the need is now a reality. I want to talk about some of my background on supercomputing. Here are a list of 5 articles that I've published, of which I'm the lead author of. The first one is the proceedings of the 40th meeting of the Southwest Decision Sciences Institute, overview of current research in global supercomputer. The second one is open source software tools for data mining analysis of genomic and spatial images using high-performance computing at the Informs workshop on data mining and health informatics. And the third one, which is in red, was at WMSCI 2012, which was 3 years ago. I was lead author of the paper, Data Mining Supercomputing with SAS Jump Genomics. The fourth one was a preceding of that, which was a research in progress. And the fifth one was visualization by supercomputing data mining, which occurred at the fourth Informs workshop on data mining and systems informatics. As my introducer indicated, I am in the process of co-editing a book titled Research and Applications in Global Supercomputing. I am in contract with IGI Global. It's co-edited by myself, Dr. Zhang, and Jeffrey Cook, and we're asking for contributing chapters. As of this instant, I do not have enough chapters to complete the book, so I am in need of your assistance in providing contribution to this book. I'm requesting a 2 to 3 page chapter proposal by July 30th.